So now let's have a closer look on these managed objects. What is this? Well, I already mentioned that we have really many different computer systems on a campus, in a company. No matter what strategy you have, you typically never have all the machines from one company. You mix. So there are very good reasons for this. But you may have problems like the very simple problem, this little endian, big endian. You learned in computer architecture that depending on the processor manufacturer, you may have little endian processors, so that was classical for this Intel world, so the PCs, or you have a big endian world, and this is the more classical thing for, let's say, it came from mainframes and all this, and but also other processor architectures, even ARM processors as well. Today they can handle both, etc. But these are the classical big servers from IBM, whatever. Then additionally, yeah, we know that today we all have 64-bit processors, we have 1024-bit GPUs, whatever, but still we have sometimes 16-bit simple controller. Think Internet of Things. We were just talking about Internet of Things. So think of these billions of devices with just maybe a simple 8-bit microcontroller. But maybe you also want to integrate them into your network management. There's no web server running this, but still maybe you want to know, so what's your uptime, what's your firmware version, what's going on in the devices. We have some problems with Snmp there. There are some more solutions. Later a bit more about this. But so the point is, we have different data representation, and the problem is if you store it in this internal proprietary format, we have to recode the data to collect it, because otherwise we don't know what it means. So we have to define how we code it, and in a way that we retain the meaning, the semantics. So we need certain exchange standards. And one of the ideas here is that, okay, we describe the content in a abstract notation. It's called abstract syntax notation 1. And the idea was, yeah, there will be 2 and 3 and whatever. Okay, but it stayed with this 1. And because we cannot simply transfer it directly, where do we place the 24 bits or the 16 bits or our very simple 8-bit controller just monitoring the temperature, whatever. So these are our native representations, little endian, big endian. So maybe this one is a little endian machine and a big endian machine. So that doesn't work. So the idea is we describe it in a way that in the end we know what it means, and we also describe how we transfer everything over the network. We'll learn that this is called the basic encoding rules. Okay, that's the motivation. So we cannot directly transfer bit by bit, because then what should the other side think of this bit stream? Is this now an integer? Is it a string? Is it 16-bit, 32-bit, 64-bit? Or what does it mean? Okay, first of all, how do we describe it? For this, we have ASN1, Abstract Syntax Notation 1, and that's the standardized language for completely representation independent specification of data types. So we can represent data types in a way that is independent on how this is then stored on this very specific machine. And this is then used in Snmp to describe the objects. So what we have here is we have descriptions of very elementary data types. So what is a Boolean, an integer, a bit string, etc. And this is octet string, so these are bytes. So the telco speak of bytes is octets. And then International Alphabet number 5 strings, so ASCII, similar things. So that is the idea. of describing what does this mean. So we have now bits, but this is now an integer, or this is a Boolean. So this is a precise definition what we mean with these bits. And then we have some more data types like set, sequence, etc., like a choice, and so on. So that is the idea that we can then have more complex data types by combining. So an employee, for example, is a set, so it's an unordered set of, in this example here we have a name, and the name is then an AI5 string, so AI5 that defines 128 characters, and so that's the name, and the age is an integer, and your person ID, for example, is also an integer. Okay, this allows the age of minus 23 years. Okay, but just an example. So that's the idea that you define data types. Because just think of programming languages. Data types, they're defined in different ways. But this has to be quite precise and clear. What do we mean if we transfer temperature value, that this is now, for example, integer, etc. So just some more examples. You see here integer, it's assigned 32-bit octet string, an object identifier. Will come back to this. And so many things already defined by ASN1, but as you see, people from the internet, they were not that happy. So they came with this structured management information. We need a bit more, like a counter, for example, like an IP address. IP version 4 bytes, also 6, and many, many more things as you see here. So there are a lot, and this is just some examples, data types. So now, what do we do? So in the end, it works as follows. So we describe in an abstract way, the data type. So for example, our integer. Okay? And then we all know that from vendor A, the computer has the native syntax. Native syntax, that means you store, let's stay with our simple example, you store locally everything in little endian. But you know that this should be an integer. Then, and we will see the example, we describe in an abstract way when we describe this managed object, for example, the buffer fill status, we describe it formally using ASN1. So we use ASN1 for the description. Locally we store it on computer A as little endian and in computer B as big endian, for example. And then the problem starts if we transfer it. We cannot simply transfer the bit stream representing the little endian, taking our bits over the line. Because then on the other side, well, the computer B will store this but interpret this as big endian. This is chaos. So no, we shouldn't do this. Okay, so what to do then? So we do not transfer our little endian, but we will code the little endian in a so-called transfer syntax. And how we code, that's defined by the basic encoding rules. So we have certain rules telling us, okay, you have abstract definition, an integer. You have to code it in the following way for transfer. And then it's up to computer A to take its little endian native syntax, knowing that this is an integer. Okay, this is an integer. Then, following the basic encoding rules, it will look like this. And this is then clear, unique, following the encoding rules. And if the computer B receives this, the computer B notices immediately, this is an integer. Why? We'll see in a second. So it's an integer. We know what an integer is because we know ASN1. We know the coding, we know the basic encoding rules. This means we can then map this onto big endian for our local native syntax. So that's the basic idea. So then it's quite clear that we on both sides understand the same thing, like this is an integer or this is a string. So this is very powerful, ASN1, BR. It really covers many different data types, etc. So you can compare this a bit with host to network, network to host. These are functions you will find on all computers, and this is what you need if you transfer something, an value, an integer, for example, over the internet. You see, yes, very powerful, ASN1, BR, etc. But again, the simple solution here, RFC 1700, is host to network, and we have a version short, 16-bit, long for 32-bit, and H to big endian 64 and big endian 64 to H for 64 bits. So there are different functions for 16, 32 and 64-bit, and this converts in the end the local representation host to the network and vice versa. And if your host is already a big endian machine, this function is basically no operation. You don't have to do anything because the transfer syntax in the internet is big endian. So this is basically a solution for integers, integer only. ASN1, BR, etc. is for many different data types. But as always, what do you typically do? Well, we transfer some integers and everything else is characters, etc. So, but it's important for integers because we have little endian, big endian. Then you have a special solution for this. Host to network, network to host, solves the problem, that's it. And this is why we typically use exactly these functions, and you will find them in C in all the libraries. We've done this with socket programming and all this in the bachelor course. So, you see, this is comparable. But back to Snmp and to this bit more powerful methods, ASN1, basic encoding rules. So, we need a way to represent many different data types. And this is done as the following. This is a classical type length value setting, TLV. What does it mean? First, we describe the type. So for our simple example, internet, host to network, this was only integer. Here we can do a lot more. We can say, is this what different classes? So there are different classes of, well, data types, universal, application, context specific, etc. I won't go into the detail, look up the standards. Is it a primitive one or is it constructed? So for example, if we have an integer, then we have a certain type that we say, okay, that's of a universal class. We'll see this example, and it's primitive, it's not constructed, it's just the integer. And then we have to say, okay, what is it? It's an integer, and we have to say how long it is and the value. Okay, how does it look like? It's not that complicated, so you simply say, I want to store a 5. And then you have to say the type, and this is then in the end 2, and 2 stands for integer values. It's primitive, it's not a constructed type. Then you have to say, okay, how long is the value? In this case, how many bytes do we need? We need only 1 byte, that's the length, and then we specify the value. It's the 5, 101 is the value. So you see, that is a way of transmitting our integers. So, and then as all the machines, they understand ASIN1, and so the machines understand the semantic, and then you can actually take this value, you know this should be integer, and now you can store it locally as int whatever. Maybe you have a 64-bit machine, but you know this should be a 5. Then you have to take care that this really is a 5 on your local machine. Maybe you only have an 8-bit controller, then you cannot have 64-bit integers, then you have to store it locally with whatever programming language you use, 8-bit, whatever. So that is the idea, and that's the way how you can exchange arbitrary data while keeping the semantics. So what is the meaning of this bit stream? Yes, it's a bit more complicated, type, length, value, but it's quite flexible. And the example with host to network, network to host, is only for little endian, big endian problem on the machines. Okay, so that is the idea of transferring the information, how to handle the problem of heterogeneous machines. That was our core problem. If we all buy only from one manufacturer, we don't need all this. But that's not the real life. Okay, now we know how to describe the content of the managed object. But how do we find managed objects? So where are those managed objects and what to do, how to structure them? Well, let's have a closer look into managed objects. What is this? And this is a real, let's say, a bit a strange word. So in the end, all atomic elements that are managed in Snmp, they are called an object or a managed object. And this was the time 80s when we talked about objects and agents and whatever. You find this in many other also programming concepts. So we have the object, the managed object, maintained by the agent. So the agent monitors managed objects. And these are basically our resources, like buffer fill size, like CPU temperature, whatever, as an example, like name of system administrator. Or like, look up this example, that's the identifier, how does this look, of our university. So you basically can find in a structured system, in a structured way, all different types of information. Okay, how? Okay, I will show you. So first of all, there are many, many different managed objects. Buffer fill size or a university. Okay, so university maybe owning then other network resources, etc. So the managed objects, they can have a very strange and long name, which is quite unique. So ISO, org, DoD, Internet, management, that's the string. I will show you some more examples. Management information base, system description. Okay, this pretty sounds like this could be a tree, and indeed, again, our strange computer science trees. So we have this root, and in the root we can go down a path ISO org. We also have CCITT, that today it's called the ITU, International Telecommunication Union. So the tree is larger. And we can go down, management information base, system, etc. So all this is part of a huge tree structure, structuring all these different types of managed objects. So all the managed objects can be identified by a unique ID or name. And up here you see an ID. You see the ID of our university, and because this is an object, it's called an object identifier. And there are many databases where you can look up what does it mean if you type in this 1.3.6.1.4.1.18,898 on what this means. So managed objects, they have a unique identifier, either in this dot notation, so that is one way, or you can also actually say iso.org.etc.mib.system. Whatever. That's maybe more human readable, but for the machines 1.3.6.4 etc. that's also fine. So that's the idea, first of all, of a unique name. Then we have the syntax. You learn ASN1, we have data types, integers, etc. Then we have maybe also description of access rights. I will give you examples: read only, read write, and then some are mandatory, some are optional. So that's the idea. And all this is stored in a management information base, and this is then also called the management information tree. And all the managed objects, they have a position in this management information tree. Okay, management information base. Is this one huge database? No. So the machine stores only a part of the tree. So maybe only some parts down here. And all the different machines, they have only their parts. There is no central tree stored somewhere. It's basically a distributed and a virtual database. So there's not the big database, but all the devices, they store a part of the tree they are responsible for. So the part they write, for example, their temperature values, their logs, their buffer fill size, etc. So that's the idea. So management information base, this is our collection of all the objects. But the MIBs also define the capabilities of a device that can be managed. So you cannot change things that do not exist in the router, for example. You cannot change the color of the output or whatever. It's a router. So managed objects monitored by agents, stored in a management information base, and the structure is the management information tree. I know a lot of terms. And also this dot notation but it's not made for humans. It's made for machines, for management platforms. And then it's fine, but still, it's also error prone. So it's a problem. You will see. So how could this look like? For example, you describe a certain object. For example, it's a string and it's a read only and it's mandatory. So this could be our abstract description. So we know how it looks like. It's a string of a certain size, read only, etc. And then there's a description, and it says, okay, this is whatever description of something, maybe the hardware type and who's responsible or whatever. So there is certain metadata for all the managed objects, so that everyone knows, okay, if I find a value in there, what is it? It's a string. Okay, it's read only, and the meaning of this is this and that. So that is one of the ideas. Okay, so, and this is the data for all the managed objects, so that you know how to handle this. And then this managed object is maybe down here, deep down here. So, for example, if we want to find our university, it was this 1.3.6.1.4. We have here 1 dot, and here we have all the organizations, and then we have the 18,898, And this is then the identifier, and attached here is then Freie Universität in Berlin. So that is, for example, a absolutely unique identification of this managed object. This would be a typical example for something that is read-only. You cannot change it. So that's the idea. Okay, so some parts of it are called here in this private subtree. And here we can do proprietary things on our own. This is a huge subtree, a huge thing. And then we have others like directory management, experimental, etc. And there we need the approval of the IETF and the Internet Architecture Board. So there we need the OK. And you see, Department of Defense, there can be also other sub-branches, and ISO, and there was also ITU, and they can do their own stuff, etc. So this is what we are looking here at, is only the internet world. We always think, oh, the internet is the network. Yeah, there are some other networks. But that is the idea here. And you see here proprietary objects, and this is our distributed database. And each agent has only a piece of it. And in the end, the object itself is all down this tree and attached to one of the branches and has then its own identifier. And so if you will find the object, basically you have to go down all the way. Some more examples will follow how we do this, how we find exactly, how we really describe exactly this specific object. So an abstract way of describing what we mean. System description is a certain object with a syntax, with an access, in this case read-only, with a certain status and a certain description. And you will find this managed object somewhere down there in the tree. So this is how it all started. Pretty soon we had the MIB-II, so newer versions updated by some more RFCs. And the version 1 that was quite short-lived. And MIB-II is a generic management information base for really many devices in the internet. And so it has a certain prefix. And you see we are already down the tree a bit, ISO, org, and so on and so on. And then the huge MIB-II subtree follows. And this allows, you see how things growing, for example, asking for many things from the IP protocol, the TC protocol, UDP, etc., etc. Oh, Snmp itself, and many more. That more than subtree has how many branches? More than 270, whatever branches in there, and those have again many branches. So the idea here is we can define here under this internet management MIB-II new, well, we have a lot of new entries here, and then there are some more for experimental management information bases, for vendor specific, etc. And a simple example is if you want to know what's going on, battery aging, you ask for 1.3.6.1.2.1.233.0.5, and there you will find in a standardized way how is this described, battery is aging. Or if you want to know where is a device, you ask for 1.3 and so on, and then you get the system location. And again, the SMI describes how does this look like? I mean, this is most likely a string, a read-only string, etc., telling you where a system is. Oh, that's first floor, room 200, whatever. Why do we do this? Because then, with a simple script, we can read out the location of all the devices we have on our network. We only ask all the time here, exactly for this identifier. So we go through the agents in the devices and ask for this identifier, the value, and then we will get back the location. And that's one of the ideas, to have a unique identifier for a certain purpose. Okay, but the disadvantage, well, it's obvious. So it's a tree, and this notation is not really the current state of the art. But this has been grown, I mean, historically since the late 80s until today. And over years, we had new demands for other functions. And one was the idea of, why can't we already collect certain information, data, statistics on the device and do some let's say, averaging, for example, partial evaluation. And this is exactly where I have remote monitoring, RMON. RMON, that's basically a management information base with some more advanced functions. So was the idea of RMON, and there you can really collect certain things, so the agents can do a lot more, can already do some pre-filtering on the devices, can evaluate things, can do packet capturing and all these things. So we shift a bit of the intelligence from our management platform to the agents. Why? Because the devices are now more powerful, and if the devices are more powerful, they can do more. And an example for this is, I want to have a counter that checks how many packets are bigger than the normal MTU of 1518 bytes. So for example, okay, these are oversized packets, and then I can let the agent do the work. And this, for example, that's our classical case for counter. Counter, so it's not an integer, it cannot be negative, but it's a counter that simply increases. It's read-only. Yeah, you cannot set the value of oversized packets because the device counts the oversized packets. For example, then there's a description, okay, total number of packets received, longer than, etc., etc. So you know what it means, you know it's what type it is, it's a counter, it's read-only, and you see this is then in this sub branch ether stats entry. Okay, and that's then the number 10. And you have many of these unique objects, and they are then part of this huge tree. Okay, I know this is just the surface of this network management, but you could have an own course only network management. But you should know at least, so why do we need something like an abstract syntax? And you will find the idea of abstract syntax in many other situations. So why do we need something like ASN1? I won't say that ASN1 is the best way of doing it, but okay, that's the way how the standard works. And what else could we do? And I gave you an example what is done. If you have these classical sockets in the internet, you have to transfer something, and there's one case that can be solved in a different way. But ASN1 and basic encoding rules, it's way more flexible. And then you can do something on your own. For example, what is the identifier for all Ethernet-like interfaces? So try to find this out. So what is the identifier? It starts with 1.3.6, but then what is it? How can you find this out? And why could, for example, the identifier given here, I will not read it, why can this be quite important? It depends on the type of devices you have, but this could decide upon, can I watch a video with high quality or not if I'm sitting in front of a hotspot. And then finally, what was the idea of RMON? So what is the additional functionality there?